Today we're going to talk about shifting, reflecting, and stretching graphs, better known as the transformations of graphs. So we are going to build and transform functions from existing functions. Let's dive straight in. The first type of transformation is going to be a translation. A translation is a shift, left, right, up, down. A horizontal shift, left and right, is a change in x inside your function. Anywhere you see an x, there will be a plus or minus a value. So if it says x minus a number, that's going to shift that number of units to the right. And if it says x plus a number, it's going to shift that many units to the left. So it's kind of backwards of what it looks like. So if your original function was y equals x squared, and I say y equals x minus 1 squared, that shifts to the right, 1 unit. If I said y equals x plus 1 squared, that shifts to the left, 1 unit. Vertical shifts are a little bit more of what you'd expect. Your whole function plus or minus a value on the end or at the beginning, or maybe in the middle, who knows. If it's minus a value, that's going to shift that value of units down. And if it's plus a value, that'll shift that many units up. So going off of my y equals x squared, if I said y equals x squared minus 7, that's going to be a shift of 7 units down. Whereas if I said y equals x squared plus 3, that'll be a shift of 3 units up. Oops. There we go. Next up is reflections. There are 2 ways to reflect. You can put the negative out front of your entire function, or you can put the negative inside the function anywhere you have an x. If the negative is out front of the entire function, that reflects across the x-axis. If the negative is inside with the x, it reflects across the y-axis. So going off my y equals x squared, if my function is y equals negative x squared, that's a reflection across the x-axis. Whereas if I put that in parentheses and then square it, that's a reflection across the y-axis. And then stretching and shrinking. We're going to use the value a. A has to be a positive real number. If it's a negative number, then we look at the reflections, then this part. Or this part, then the reflections, either way. So if my a value is in with the x, we stretch if a is small. So if a is between 0 and 1, it is a stretch by a factor of, notice that that's just the reciprocal. A number in with the x is a shrink if that value is greater than 1. Notice that we ignore if it is 1 because then there's no point in writing that value and it's not a change. So if I said, all right, we're working with x squared, right? Y equals 1/3 x squared. That's actually a horizontal stretch by a factor of, so FO, 3, because it's the reciprocal of 1/3. If I said y equals 4x squared, that would be a horizontal shrink by a factor of 1/4. All right, so kind of the opposite of what it seems. Vertical stretches and shrinks are exactly what they seem. It's a stretch if that a value is bigger than 1, if the a is out front of the whole thing. It's a shrink if that a value is between 0 and 1. So if I use y equals 3x squared, notice that that 3 is not in with the x. It's not squared. It's just a 3. That is a vertical stretch by a factor of 3. If I said y equals 1/8 x squared, well, that's between 0 and 1, so that's a vertical shrink by a factor of 1/8. That just means it's 1/8 as tall as it was before. All right, so some steps to graph multiple transformations. And there's many different steps you could follow and still get the right answer. The way I'm going to discuss, we're going to use this order. We're going to do stretches and shrinks, reflections, and then translations. So if f of x equals a times b times x minus h to some power or whatever function we have plus k. All right, my stretches and shrinks are a and b. My reflections are also controlled by a and b. My translations are h and k. Now this little box, you can't actually see it, but this is different than writing it like this. For this one, we would have to do a horizontal translation and then the other ones. So we always want to factor this b out. Oh, sorry, I had it cubed there, didn't I? There we go. We always want to factor that value out to follow these steps. So we have a function given. We need to identify the parent function and then list in order the transformations applied to the function to get this graph. So the parent function should be a pretty simple step. W of x is negative x plus 1 cubed. Well, that's formed from y equals x cubed. That's our parent function, right? PF. All right, now transformations. We want stretches and shrinks. There are none. Reflections. I have a negative out front. That's a reflection over the x-axis. And then we have shifts. We have a plus 1 inside with the x. That means it's left and right. It's a plus, so it's left, 1. Shift, left, 1. All right, next one up, we have k of x equals square root of x plus 3 plus 1. Well, my parent function, call it PF, is y equals the square root of x, that basic function that we'll know that we're going to base everything off of. We don't have any stretches or shrinks because there's no multiplication. No negatives, so we don't have any reflections. We just have our shifts. We have a plus 3 in with the x, which means we shift left 3, and a plus 1 outside, which means we shift up 1. Next up, n of x is the cube root of 0.5x minus 7. Before we do anything, it's a good idea to factor out this b value. So it's still inside the cube root. I'm just going to factor out a 0.5. So that leaves me an x minus, think about 0.5 times what makes 7? It's actually 14. Now I can say my parent function is y equals the cube root of x. I see a multiplication, which means I have a stretch or shrink. It's inside the cube root, so it's a horizontal. It's less than 1, so that means it's a horizontal stretch by a factor of the reciprocal of 0.5. Well, 0.5 is a half, so the reciprocal of a half is 2. Then we do our shift. That's this 14 now. So we shift. It's a minus inside with the x, so it's to the right. 14. All right, so next up, I have h of x equals 2 times negative x minus 3 squared. First thing, very first thing, this is our b value, right? It's a negative 1, but it's not factored out inside there, so we need to factor it out. Negative x plus 3. That switches the order of our transformations and switches what it's going to look like. So we start with parent function. Our parent function here, we have y equals something squared, so it must be x squared for our original function. Stretches and shrinks. Well, there's just a negative in front of the x, but a 2 out front. So that's a vertical stretch by a factor of 2. Now I deal with this negative. It's inside the square, which means it is a y-axis reflection. Reflects over y-axis. And then I have my plus 3. That is a shift left of 3. All right, g of x equals 1 over x minus 5. This time, my parent function is actually y equals 1 over x. That's one of our basic parent functions. All I see is a minus 5 in with the x in the denominator. That means it's the left and right, so it's a shift. It's right because it's a minus of 5. And then last but not least here we have f of x equals 1.4 times the square root of 1/4 x minus 14. The minus 14 is outside of the square root, you can see here. So our parent function is y equals the square root of x. Start with our stretches and shrinks. I'll go left to right. I have a 1.4 outside of the square root, which means that is a vertical stretch because it's more than 1 by a factor of 1.4. I have a 1/4 in with the x, which means it's a horizontal stretch because it's less than 1 of the reciprocal so it's a factor of 4. So this one is taller and wider. And then we have this minus 14, which is a shift down of 14. This time we're going to write the function. So I have 5 units left, horizontal shrink by a factor of 1/4, and a shift 1.5 units down. Now this says in the given order. We're going to ignore that part. So we're really going to deal with the shrink first and then our shifts. Our parent function is y equals the absolute value of x. So a horizontal shrink by a factor of 1/4. That means our b value is the reciprocal of that, which is 4. So in with the x goes our b. So I have the absolute value of 4x. Then I shift 5 units left. That's a plus 5 in with the x. And make sure you put it in with the x. All right, don't put it outside of that 4. You need another set of parentheses there. And then I shift 1.5 units down. I can just stick a minus 1.5 on the end. All right, my parent function this time is y equals x squared. I'm going to shift 2 units right, stretch vertically, reflect, and shift 5 units up. Again, we're going to take 2 and 3 and bump them up to the top because that's what we do first. So a vertical stretch by a factor of 3 means that our a value in the front is 3. So that makes it 3x squared. Reflecting across the x-axis just sticks a negative in the very front. So we actually have negative 3x squared. Then I shift 2 units right. That's a minus 2 in with the x. So that's negative 3 times x minus 2 squared. And then 5 units up is just a plus 5 on the end. All right, this parent function is y equals x cubed. I'm going to shift it to the right and reflect over the x-axis. Again, pump that up to the top. Reflection over the x-axis sticks a negative in the front. Negative, there we go. And a shift of 4 units right is a minus 4 in with the x. So we have negative x minus 4 cubed. Next up, our parent function is y equals the square root of x. We have a horizontal stretch by a factor of 4, shift 3 down, and 8 up. So a horizontal stretch by a factor of 4 means that our b value is the reciprocal, which is 1/4. So that means in with my x, so inside the square root, I put 1/4 x. To shift 3 units down, I subtract 3. And to shift 8 units up, I add 8 outside of it. But I could simplify this. Because if I'm shifting 3 units down and then 8 units up, I really am just shifting 5 units up. So I have the square root of 1/4 x plus 5. All right, now we're going to write the equation based on the graph. I like to draw a little. This first one, I can tell that my parent function would have been y equals x squared. So I'm going to draw what that graph looks like a little bit. Just a couple important points there. All right. First question is, did I stretch or shrink at all? Well, if this was 0, 0, I have 1, 1, 2, 4. I don't have any stretches or shrinks. Reflections? I don't see any. It looks the same. It might have been a reflection over the y-axis, but I don't care because that would be the same. I shifted it 4 units left and 2 units down. Oh, sorry, 3 units down. So that's all I have to add to it. So y equals x plus 4 squared minus 3. All right, next up I have this one. A V-type shape is based on the parent function of y equals the absolute value of x. So the absolute value of x usually looks like that. So I can tell I definitely have a reflection over the x-axis. And if I did that, let's switch colors here, it would look like this. Now I can tell that this is skinnier. And I can choose to either do a vertical stretch, making it taller, or a horizontal shrink, making it skinnier. Those do the same exact thing. I'm going to do a vertical stretch because what should have been -1 is actually -2. What should have been -2 is actually -4. What should have been -3 is actually -6. So that means I know I have a vertical stretch by a factor of 2 because everything is doubling in height. I don't have any shifts going on, so we can dive in. Our function, a vertical stretch, goes out front. A reflection over the x-axis also goes out front. And I have the absolute value of x because I didn't have anything else going on. And for this last one, we would start off with our parent function. In this case, our parent function is y equals 1 over x. That function, generally speaking, looks like this. All right. So I can tell I definitely had a shift, right? I definitely had to scoot it over 3 to the left. Now, vertical stretches and shrinks are a little trickier on this one. Look for a point. Well, first of all, look for those asymptotes, right? Those invisible lines that you don't quite get to. They're usually the 2 axes. So I pretend these are the 2 axes. The point 1, 1 should be on my graph. If it is, I don't have to worry about it. There's no stretch or shrink. If that point was 1, 2, then it's a stretch by 2. Same thing down here. I could do -1, -1. So my function just had 3 left, which makes it y equals 1 over x plus 3 in that denominator with it.